Everyone, it's Michael from the Nautilus Group, and I'm back to explain the Chapter 1 assignment, questions 6 and 7 for CST 311. I'll go a little quicker on some of my explanations, as I'm assuming you have already watched the video for questions 4 and 5. If you have not, I encourage you to go watch that video as the two relate to each other. So once again, we have the same given information as we had for questions 4 and 5. So we're looking at that same network scenario where we have k number of sources. We have several sources that are connected up. They've got their capacity links of the source, which is RS. There's the capacity link of our destination, RD, and then we have a shared common link, R, for the internet. So question 6 states, suppose now that k equals 10, RS, which is our capacitive link for the source, is 100 megabits per second, RD, which is our capacity link for the destination, is 1 megabit per second, and R, that common link, is 0.75 gigabits per second. What are the throughputs between each source-destination pair? And they've given us multiple options. So again, our first step is we're going to put all units to the same unit. We're going to use dimensional analysis. This is very important. I've gone ahead and included some links at the end of this video for being able to understand dimensional analysis a little better and be able to see some other examples of it. If anybody is a little weak on dimensional analysis, now is a great time to become strong in that skill. It is something that you will use over and over again. So once again, for our problem, we have two that are in megabits per second and one that is in gigabits per second. And so it will make the most sense to convert the gigabits per second to megabits per second. So we set our problem up. We have the 0.75 gigabits per second over 1. We're going to multiply that by our conversion factor of 1 gigabit per second to every 1,000 megabits per second. Dimensional analysis, we make sure that they are top and bottom. This allows us to cross our gigabits per second units, cross the top, cross the bottom, and that leaves us with megabits per second. When we do the math, 0.75 times 1,000 gives us 750 megabits per second. So in step 2, we're again trying to find the relative capacity for the common link R based on the number of destinations k. So for this problem, k is 10 and R is 0.75 gigabits per second, or 750 megabits per second, as we calculated in step 1. Again, using our formula, R divided by k, we find that 750 divided by 10 is going to yield us 75 megabits per second. So now we come to step 3. We're going to compare the various capacities in our network. So we'll recall that we have our capacity link for the source is 100 megabits per second. Our capacity link for the destination is 1 megabit per second. And the shared capacity, as shared out over k number of destinations, is 75 megabits per second. When we compare that, we see that RS is the greatest, which is greater than our common link, R, which is greater than RD, which is the capacity link for the destination. So, once again, our least amount of capacity is going to be RD. So again, what does this mean? Well, we know that throughput is based on that lowest capacity. We talked about the examples before in the previous video about traffic on a street or water going through pipes. And so we know that our lowest capacity is going to determine throughput. And so since the lowest capacity is RD, then that means the throughput is 1 megabit per second. So now we're back to our original question. What were the throughputs between each source-destination pair? And so we determined that RD was the least amount of capacity, and this dictated our throughput, so we can go ahead and select 1 megabit per second as our answer. So question 7 is related to question 6, and it wants to know the bottleneck links in question 6. And we're given several choices. We have our common link capacity of R, the capacity link for source RS, and the capacity link for destination RD. So again, the bottleneck links correlate to throughput. And again, it makes sense that where we have, if our throughput is based on the least amount of capacity, then the least amount of capacity is going to relate to where the bottleneck in a network is. Those go hand in hand. And it's pretty logical. Even calling it a bottleneck link, I think, is a very logical term. As computer scientists, we like self-naming, conventions and terms and things like that. So once again, RD is going to be the link with the lowest capacity, and that is our bottleneck link. So question 7, what are the bottleneck links? We're going to select RD. I mentioned that I was including some additional resources. The first one is from Khan Academy, and it's a video showing dimensional analysis through algebra. And for our purposes, you could sub the word algebra for the word term, but it's a good video. And the other is through a school, through a college university, and this was created for a chemistry class. But the examples are good, and so again, I recommend both the video and the website, as well as just go out and search or look for additional resources on dimensional analysis. Look for problems to practice. It's a really, really good skill to have, so I encourage you to do that. So that's been my video. I hope it's been useful to you. And feel free to leave any comments or feedback in the forum, and I'll respond.